Now I have the pleasure to announce Robin Phillips from Maxon. He will talk about customized actuators for Martian Mechanism. We'll now move from planet Earth. We'll leave the system where the moon is circling the planet Earth, and we go in the further planetary space, we go to Mars. And Robin Phillips has been, as a mathematician and astrophysician, working in this business of astronomy. He has been working at Maxon for quite some time. They have an aerospace group, and we are very excited to hear from him what a Swiss company, Maxon, in Sachsen, can contribute to Mars. Please, Robin, you have the floor.
So, welcome to our talk about Maxon's activities for Martian mechanisms. There's a big push, as I'm sure everybody knows at the moment, to use COTS, or commercial off-the-shelf actuators, as much as possible in special applications. So we're going to be concentrating on how Maxon has approached this market segment. And of course, it's not possible to ever use directly COTS parts. They always need some customization. So we're going to have to look here as to how we go about doing that, with an emphasis on our Martian applications. Before we go into that, I think it's always important to understand why we're doing this. So I would like to just give a quick background as to why are we going to Mars and why are we making the effort to build actuators to function there. So if you look at the picture at the top left, that's pretty much the best picture that could be taken at the middle of last century from Earth-based observations. And you can see it's a planet, so we knew that, but really it's not possible to say very much more than that. So at the very beginning of the space age, we quickly got to the point where spacecraft were being sent to Mars. The first spacecraft that just flew past, there was no way to break them into orbit. They just took a series of pictures as they went past, and there was quite a lot of disappointment at the start that this was just a cratered landscape. But going back a few years later and going into orbit, we then discovered there was a rich variety of geography on Mars to be studied, including volcanism and these canyons. The next step is then to get down onto Mars, because no matter how good your camera system is from high up, you can never really determine everything that you might want to. So there was a very large program, the Viking landers, which landed in 1976. With these, you can see those are the first motors, not from us, but at the time Maxon wasn't doing the special motors on Mars for the arms and digging the trenches, and there was a lot learnt there. Then there was a fairly long gap until the 1990s before the US decided it was time to try and go back again. And this time the aim was to go back with rovers, and then it's maybe worth considering why are we going back with rovers, and it's mainly just because you have to land somewhere safe, and the safe place to land is usually not the place that's most interesting, because you want somewhere flat and I'll say boring, so that you can get down safely. The lander then of course is stuck, but if you have a rover you can then drive to the interesting locations in the mountains or in the canyons, and that's fundamentally the reason for going with rovers. Then you have to think about what technologies do you need to be able to get a rover there. Communication links have been obviously functioning for decades, so that was a known reliable technology. Power comes from batteries, solar cells, or nuclear power on Mars. Again, that had been demonstrated for decades previously. You need to be able to navigate, so you need camera systems. That was all fine. And the aim of all these systems, of course, is to get your science instruments to the targets. But what was missing now, and what was new in the 1990s, was motorization, to be able to reliably drive around on Mars. And this is where the story of Maxon with JPL starts. They came to us in the late 1990s looking for a simple way of demonstrating rover technology. So that's what the Sojourner rover was all about. And that's what we would now call an engineering model. You want it as simple as possible. You don't want to spend too much money. You're not too worried about the science. You just want to demonstrate the technologies. And Sojourner demonstrated that very well. So then it was possible to go back with Spirit and Opportunity. This time it was 2 different motor types that were then coordinated across the entire rover. I particularly like to pick out this picture on the right here, was again to remind ourselves we're going there not to do engineering, we're going there to do science. And the aim was to see whether previous signs of water could be found. And the sedimentary rock that you see here is, you don't need to be a geologist to understand that's clearly a proof that water, or at least a liquid, was flowing on Mars. And as is well known, of course, Spirit and Opportunity lasted for years. In Opportunity's case, it was 15 years, and more than a marathon worth of distance is the way they like to phrase it. Bringing ourselves up to date to the current motors that are on Mars. So the latest mission is the InSight lander. And this is a joint European-US spacecraft. It's just a lander, but it has an instrument from DLR in Germany on it, which had what's called a mole in it, which a bit like a pile driver on a building site, where it rams itself into the ground by banging away on top. And if we look at the internal details here, the mole has a motor in the back half of it, which winds up a spring, and then when it releases the spring, that forces a mass forwards and it hammers its way into the ground like that. As is well known, in fact, InSight had quite a bit of trouble with the surface tension of the upper layers of the Martian surface. If you look at the top row of pictures here, the instrument was placed on the ground as it was intended to, but the mole never made its way underground properly. The top middle picture shows how then the structure was moved out of the way, and then you can see that the mole is sort of opened up a big hole in the ground, just because, as though it was going into sugar, is basically the way to think of that. Over the last 2 years, there's been a lot of effort. At the bottom left, you can see how the mole kept backing back out of the ground, how then the arm was used to try and pin the mole to help it go back down again, and eventually it was achieved by pushing on the back. And the picture on the far right is just from this week. That's the current situation. It's now fully in the ground. There's now Martian surface being piled on top of it using the scoop to get enough pressure on it so that then hopefully it will proceed by itself. The interesting thing from our point of view here is, of course, that the motor and the gearbox have received way more use than was expected, and so far everything is working fine. Coming up in 2022, this was supposed to launch this year, the ExoMars European rover. Of course, it got delayed for various technical reasons and inability to travel. But there's a huge variety of motors on here. This picture shows them for all sorts of different systems on board. The rover itself is roughly the same size as Spirit and Opportunity, but what's new is the drill that's on the front. And this is a very complicated mechanism that's able to drill 2 meters down underneath the surface in order to bring samples up for the onboard laboratory. This slide just shows a bunch of the different mechanisms that we have. So at the top right, there's this sample tray which transfers the samples from the drill inside the rover to the laboratory. Then it goes into this crashing station at the bottom right, which is 2 plates that move backwards and forwards like this and crush the rock to turn it into a powder. The powder gets put into a carousel with a bunch of different ovens on it, and then the ovens have lids that close on it. All of those are mechanisms, all of those need motors. The main drive system on the rover, so we're showing the Bogie system here. There's 3 large actuators on each wheel to deploy it from its folded up position during flight, steer and drive. And this was built by us. It was designed by our collaborators in Canada, MDA. Internally it has a motor, a gearbox, a brake and an encoder, which is the combination you see on the right there. So MDA and Maxon worked here together to use MDA's expertise in how to design large actuators together with Maxon expertise in series production, as we built 70 of these in total across the entire program. The picture at the bottom right here shows the 9 flight unit lots for the drive wheels with heaters on them and all the wiring and the like, which was all done in our facilities here. On its way to Mars at the moment, we have the Mars 2020 rover. Its task is going to be to drive around on the surface of Mars to interesting locations, collect samples, package them up into these tubes that you see lying on the ground there, and then deposit these tubes on the surface of Mars. Inside the rover there's a very complicated handling system which will handle these tubes and the samples, and the end effector, so on the end of the arm that moves these samples around, there's a gripping mechanism, and that's driven by this unit that you can see on the screen here. This can probably be considered one of our most highly customized units. It looks completely different to what we have in our catalogues, but the core is exactly the same. The two motor gearbox pictures at the bottom left there are the catalogue products. And if you were to look inside those, the stators, the key gearbox parts, the gear teeth, they're all the same as in this super customized version. And that's really the idea here. We take the catalogue parts where we have the heritage, so through having built hundreds of thousands of copies for industry, we modify them by knowing what we need to do to make them vibration and shock resistant and the wide temperature ranges, and then apply the modifications as our customers need so that the mechanism actually works for them. And you can see here again the non-exploded view on the right. That's what it really looks like, and the core of that is the same as the two parts on the left. It's the same principle here with this, what we can term an engineering model of the Mars helicopter, which is also attached to the Mars 2020 system on its way to Mars. The DCX units, so small brushed motors that you see at on the right there, look very similar to what you would see for any Earth-based industrial application or medical application. And they just have key modifications on them. In this case, it's to enable it to control the swash plate, which is what controls the blade angle on the helicopter. So this is almost certainly going to get the highest amount of publicity in February of next year when it lands. We do a lot of the environmental testing and qualification that is required to show that these designs actually do work. So we obviously apply our knowledge from previous projects. But you always have to go through this process of building engineering models, testing them in the laboratory, finding out what works well and what doesn't, then building your qualification units, performing a formal qualification test on them, which can include these systems that we're showing here or others, and then ensuring that you build your flight models exactly the same way as you did the qualification models. So I just want to finish off with a quick overview of what Maxon is as a company, and then how we're dealing with the issue of combining large series production that we do for Earth-based applications and the special stuff that we do for space applications. So, as this slide shows, Maxon is nestled in the foothills of the Swiss Alps. There's about 1,200 people working here in Switzerland, and close to an additional 2,000 worldwide. And I think the key thing maybe to pick up on this slide here is we produce 5 million motors a year, but in 16,000 different variations. So if you divide 5 million by 16,000, then you realize that the standard lot size is not very big. So we really specialize in all the niches that nobody else wants to deal with. We've turned ourselves from just a family-owned Swiss company into one that's really active worldwide over the last couple of decades, and we now have factories scattered all around the world in order to provide optimal local support. We do both brushed and brushless DC motors, the difference being as to whether you have the winding spinning or the winding stationary. And a series of gearboxes in sizes, as it says here, from 4 to 58 millimeters. And that's where we basically go and take our core parts from that we then do the customization from. We started off by having a business unit system where the space applications were inside the aerospace business unit. This is an example of the kind of work that we'd be doing for the aviation side. And we fairly quickly discovered that trying to mix the large volume aviation products with the low volume high engineering requirement space products was always causing us conflicts with resources. So we've now split this apart, and we have what we call a space lab, which is a small group of about 10 people across the company, where we specialize only in the space applications. And this, I think we can really recommend this scheme. We based it a little bit on the idea of what Lockheed did at the end of the Second World War with their skunk works, where you take the resources, you split a group off from the main company, you take the resources that the company has, but you run them with a different set of processes that are more aligned for the specialist high R&D applications and not so much series production. And we're finding this is working quite well for us now. Just to give one final example of kind of other applications that we do. Coming up next year, there's a mission to Jupiter, the Lucy mission. There's a mission critical deployment application in there that we have a redundant motor system for. That's what you can see on the right there. And the process to get there was, we started off with our catalog product. We first had an aircraft application that we developed this for, where we figured out what we needed to do to add the vibration and shock resistance. We could then use that basis when we developed the ExoMars wheel drives, and that's what was by basically doing the space rating of all the materials and processes. And then now we take the ExoMars design and we simplify it a little bit so it doesn't have maybe quite so much of the exotic production steps in it, but has all the basic design in it that we know works for the vibration, the launch, and the temperature cycling. And that gives us a modified catalog space product, which is now available to anybody, and which we can offer at much lower prices than doing a fully customized version. And that's really our goal for the future. We have these sort of additional areas that we're looking at. There's manned spaceflight, which is now coming. We are running with an ESA project on that for the IBDM system. There's of course all the new space companies, of which SpaceX is an obvious example. Every Dragon that goes to the space station we've been involved in since about 2010. And we're not going to neglect the science missions either, and things like Lucy will continue to come. So I hope you found that interesting, and thank you for listening.
Thank you, Robin. Thank you, Robin. Pleasure to meet you. It looks like you moved from Saxland on the Lake of Sarnen directly to the Mars.
Yes, I'm looking for Matt Damon, but I haven't found him yet.
How does it feel when the gravity is only 3.7 in Mars and not 9.8 like on planet Earth?
Well, it means there's a lot less stress on my old bones, in the same way that there's a lot less stress on the parts of the vehicles that we're sending to Mars.
Yes, people have asked us about testing. You showed some images about testing at high temperature, low temperature, high pressure. But let's confirm you have no Mars atmosphere to test the machine in Saxland altogether. You can only take like special elements like the temperature, like the pressure, or like the gravity apart.
Well, the gravity we can't do anything about, but everything else we try and test simultaneously. So we have a vacuum chamber, we put a leak valve on it, and we leak CO2 in to simulate a 8 millibar atmosphere. And then we have a cool plate inside the chamber, so we cool that down as well. And so we really can simulate everything except for the gravity.
And gravity doesn't have a major impact on the performance of all your little motors?
Well, it's always dangerous to say something doesn't have an impact. There's nothing that we've discovered so far on motor level where that's important. The InSight mission is a classic example of where you see that the problems they're having getting the mole into the ground are undoubtedly related to the 1/3 gravity.
Yes.
That wasn't tested properly on the Earth.
Yeah.
The Mars helicopter is tested with a so-called gravity compensation system. So JPL take the complete helicopter, place it in a very large vacuum chamber, and then they have a sort of a rope connected to the ceiling. They have one of our motors on the ceiling as well. And then that pulls with a defined amount on that rope in order to compensate for the gravity.
But let me ask a stupid question. You don't have much air on Mars, do you?
8 millibars as opposed to about 1,000 millibars here.
And
so
a helicopter can carry load?
Yes, it can carry a load, but not very much. So it has very big blades, and every gram is looked at, and that's why these motors that we had were of interest to them, because the power density in these motors is very high.
I know that our helicopters have problems to go to the higher mountains in Switzerland and are impossible to go to the Himalayan 8,000 plus.
Yeah.
Could they use your Martian helicopters and then they could go to the top of the Himalaya?
Well, that's because it's just what you design it to, right? The helicopters here on Earth are designed for normally being used at sea level or not too far above sea level.
Yeah.
And you're trying to maximize their payload. If you were designing them for Mars, you'd put much bigger rotor blades on them, and you'd have to cut back the amount of payload a lot.
You should have extendable blades that you can retract once you land on the sea level. Okay, it was a pleasure to see what you showed us. It was a pleasure to talk to you. I'm happy to announce that tomorrow we have a special session, a discussion with you. Therefore, I cut this discussion relatively short. At 15:50, that's something like 3:50 p.m. tomorrow, we'll have a 20-minute discussion time. Myself will talk to Robin, and my goal is to learn about what, from this fantastic profession you have, what can be taken for engineers, for young engineers when they plan their future. You're not just doing exciting products, but you're also sort of a model career between an astronomer and a mathematician, and you deal with elements that are eventually very important for us on planet Earth to save energy. Thank you very much for joining us, and we'll see you again tomorrow.
Thank you.